Now we're going to turn our attention to looking at a couple different pieces of terminology and important theorems that are going to help us relate the concepts of conservative vector fields and independence of path, as well as some other things that we can take a look at. So again, I'm going to encourage you very strongly to have like a separate sheet of paper or something like that where you can kind of store all these definitions at once, because it does start to get a little dense here. Okay, we're going to start with this starting definition. A curve is called closed if its terminal point coincides with its initial point. So again, that would kind of be like if I had a curve out in space that started at this point, it would not be closed if it just kind of started and stopped at two different spots. But if I had a curve that started somewhere and then ultimately arrived back at the same point, I would refer to the second one here as closed. So that's a closed curve. Okay, that's important for the next theorem, because if we take a look at what this says, suppose that f is a continuous vector field with a domain of D. Then this work integral will be independent of path if, and only if, the work integral is equal to 0 for every single closed path in D. Okay, so this is a really weird sort of a result, but notice the ideas again that it's linking together. It's saying that independence of path is linked to integrals along closed paths equaling 0. These work integrals along a closed path must be 0. So the idea here that's really important to drive home is this if and only if that's listed in here. This kind of indicates that the first part of the statement can imply the second, but that also you could perfectly fine reverse the order of this. You could say if every closed path in D produces a work integral resulting in 0, then you know you have independence in path. So this is a really powerful idea. We're going to see several more ideas though here before we go ahead and move into some examples. So hang on for a little bit before those examples come about. We're going to take a look at some more definitions on the next page. We'll say that a region D is open if for every point P that is in D, oh boy, there is a disk with center P that lies entirely in D. Okay, so intuitively, D is an open region if it does not contain any of its boundary points. So here's how I try to think about this. If I had a region that didn't contain any of its boundary, then this definition is saying I would refer to this as open, because no matter what point I pick inside of that region, there's always a way that if I zoom in on it enough, oh, I'm zooming in too far. Way too far. There we go. But if I zoom in on it enough, I can go ahead and put a disk around it. And that whole disk stays inside the region. Notice even if I get really close to the edge, there's still a tiny little disk. I can slide around that thing. So this is considered an open region. A region that is not open wouldn't have this property. And that would be easy to see, because if I included the boundary and then I selected a point on the edge, no matter how big of a circle I draw around it, I'm definitely going to be collecting up points that aren't inside the original region. So this is what we mean when we say a region is open. We will also say that a region is connected if any 2 points in D can be joined by a path that lies entirely in D. So we could say that something that looks connected would maybe be a region that looks like this, because no matter what 2 points in here I select, there's a path that I can draw and actually leave them, and that path is entirely inside. I can even do weird sorts of things where, like, maybe I have like a hole in the region, something like this. Well, even if that's the case, I can still imagine that there's a path. I just have to kind of go around the hole. But I can easily imagine something that's disconnected by just saying like, well, what if this is a region? Now, if I want to get from here down to there, I can't do that and stay inside the circles. So this over here would not be considered connected. Again, these ideas are important for the next theorem. Suppose F is a vector field that is continuous on an open, connected region D. Then if it's the case that this work integral is independent of path, then F must be a conservative vector field. So if you have independence of path, then you have a conservative vector field as long as you're working with an open and a connected region. Now, normally during class, I would have gone through to try to prove this result, but I think for the sake of how many videos this section is already going to take, I'm going to skip over the explanation of the proof here. If you're interested, you can go ahead and take a look online to see kind of how this proof plays itself out. But what I'm going to do is I'm going to jump ahead to what the next theorem says, and we'll see here that we have a lot of theorems shaping up. So this is going to take some time to get used to. But here's our next theorem. If f of xy is some conservative vector field, so if I start with a conservative vector field where p and q have continuous first order partials, then throughout D, we automatically should be able to determine that the partial derivative of this first formula with respect to y should be equal to the partial derivative of the second formula with respect to x. Okay, again, these are a lot of statements and they can be very confusing to take a look at. The one question that I have here is why in the world would this actually be true? And I can actually see why it might be true. Remember that if I have a conservative vector field, that means that there's a function f of maybe say x comma y where the gradient of this is equal to my big capital F. So the big capital F is kind of almost like the first derivative, if you will, of this original f of xy. And if it's the case that I can take the derivatives of those things, then that would kind of be like my second derivative of my original f. And if my second partials are continuous, then actually back in chapter 3, we knew that the mixed partials here were actually going to be equal. So this is kind of the same idea that we're ending up with here. Of course, one of the crucial questions that we always want to have every time we see an if-then statement is, can I reverse it? That's what we call the converse. So can I actually say that if I know that these two things are equal, can I then claim that I have a conservative vector field? Well, to understand that, we're going to have to talk about, you guessed it, even more definitions. So here's another one, a simple curve. A simple curve is a curve which doesn't ever intersect itself at any point. So the idea of a simple curve might be something like this. Here's a curve that's simple. It starts and stops, it's beautiful. But a non-simple curve would be something that like crosses over itself. So this thing here is not simple. I'm going to go ahead and redraw that really quick so it doesn't just look like a 2, right? But this curve is not simple. If I have a simply connected region, then I know that that means that every simple closed curve that I can draw, simple meaning it doesn't overlap itself, closed means it stops and starts at the same spot and closes only points in D. So I can see here that like, let's suppose I have a region out in space that looks like this. Well, then I know that if I was to ever draw a curve in there that's simple, doesn't intersect itself, and closed, starts and stops at the same point, the stuff on the inside of that are only things inside the original space to begin with. Notice if I have something kind of like a donut shape with a hole in the middle, then I can't necessarily say that every time I draw a nice curve that doesn't cross over itself and starts and stops at the same points, not every point on the inside is a part of D. So the first example here would be considered a simple region, and this other one is not simple, not a simple region. So simple regions are essentially going to be things, or simply connected regions, are going to be things that essentially like don't really have holes in them. Okay, and that's what I have down here. A simply connected region is a connected region which contains no holes. All right. With all of that in mind, we're able to kind of state our last theorem for this video. And I know there's been a lot. This is one you'll probably have to watch over a couple times. Here's what it says. Let F be a vector field on an open, simply connected region D. Then if it's the case that the P and the Q, the guys coming out of this vector field, have continuous first order partials, and you know that the partial with respect to y for P and the partial with respect to x for Q are equal, then you can determine that F is a conservative vector field. Okay, this is actually a lot of information, like a lot of information. This is probably the most overwhelming part of chapter 5 in my opinion, because there is so much stuff that happened here. In this one video, we've already talked about at least 3 theorems and probably 6 definitions. That's a lot of ideas. In the next couple videos, we'll try to sort out how we can actually use these different ideas. We're going to see this as kind of like a bank of possible options that we could take when trying to answer a question. There are a bunch of different tools or strategies here. It's very similar to like lists of integration techniques that you had in the Calc 2 class, or maybe types of series or different types of convergence or divergence tests that you had in Calc 2. They were all techniques to help you answer questions. And so here we've identified a lot of different theorems and definitions that we can use to help us determine if vector fields are independent of path and or if they're conservative. So in the next couple videos, we'll take a look at some examples of these.